Now I'm just going to start off with melting some ice at different rates. So if you touch the metal, it feels cold, and if you touch the foam on the right-hand side, it feels warm. But within 60 seconds, you're going to see that this ice is going to melt on the left-hand side, even though it's on the cold metal. And the ice on the warm foam doesn't melt at all. Probably will stay there for the whole lesson, although I'm only giving this 60 seconds. And that's because metal's a good conductor. So it feels cold because it's transferring the heat out of your hand very quickly, so it feels cold. And it's also transferring the heat into the ice very quickly. And so it melts very, very quickly, even though it's you can word it in a clever way and it feels cold, but it is actually a lot warmer to the ice because it's transferring the heat into it much better. So the solid ice held together by hydrogen bonds is taking in the heat, and the kinetic energy is breaking those hydrogen bonds, the positive and negative attractions, and so they're not in fixed positions anymore. It can roll over each other and be the liquid. And this is freezing point depression. So this is the ice normally. It's fairly dry actually because it's a big block of ice. It's not melting that quick. You can see there's a little bit of water slowly coming off it. And what we're going to do is we're going to put salt on the road. So this is how they melt the ice off the road. They sprinkle it with salt, not very environmentally friendly. And so what those salt particles, the chlorine is the green and the little purple one's the sodium, that disrupts the structure of the water, the nice crystal rings. And so you can see that it disrupts it, and so it's no longer the crystalline solid structure, and it goes into the water structure, which is much more dense. Okay, so that is liquid water. Okay, and finally the last one, I'm going back to these phase diagrams just so you can understand changes of state a lot better. The phase diagrams help you understand those. So it's the pressure and temperature relationships, because temperature and pressure should always be recorded really in the room because it affects all sorts of different things in all the reactions you do. So this one, in normal substances, the slope is to the right, and so I've drawn a direct line up, and you can see if you put more pressure on it, the gas particles will be pushed together to become a liquid, and even more pressure you can push them into becoming a solid. This one's for carbon dioxide. And that's how most substances work. But water is quite interesting. It actually has the slope going in the opposite direction. It's going to the left. So if I draw a line straight up, when you put more pressure on the ice, it actually turns it into a liquid because, again, the crystal structure is broken down, and so the spaces are gone, and the water becomes much more dense and rolls over each other, and that's a liquid. And so what you do is you just leave the wire on there with all the weights on there, and it because of the pressure, it melts the ice, and then the ice, the cold water refreezes over the top of it. And so you can see that even within that short time, again, I'm not that patient, I'm only giving it a few minutes, you can see that it refreezes over. If you leave it for an hour, maybe an hour, it might go halfway through, and then it'll look really cool. So I've done that before. Don't do it too often though.